I am Amikraj Behra, a BSc first year student at CMI. Today is the second week of STEMS lecture series, and our first talk will be given by Professor K.G. Arun on the talk titled Sounds of Spacetime. Professor K.G. Arun completed his MSc in Physics from Cochin University of Science and Technology and completed his PhD from Raman Research Institute, Bangalore. He was a VASF fellow at LL Orsay and IAP Paris, and a postdoctoral research associate at the Washington University, St. Louis. He is a member of LIGO Scientific Collaboration in India and Indigo Consortium. He is also an associate of International Center for Theoretical Sciences, Bangalore. So, Professor K.G. Arun.
Yeah, hope you can hear me well. Okay. Yeah, so thank you so much for the invitation to speak at STEMS 2019. I was told we may have a spectrum of students ranging from school students to the undergraduate students, but now I see also PhD students around. But so I want to know, are there school students in this, or mostly is our own undergrads? Okay, that's fine. So that helps actually, just to plan the thing. Okay, so my talk, as you have seen, is, I'm going to talk about sounds of space-time, which is another popular way of calling gravitational waves, and that's what I'm going to talk mostly about. I have given some variant of this talk here to various school students in the past and so on. Maybe you are a new set of audience, so it's not that much of a repetition. Okay, so this is what you think about. So gravitational waves is what I'm going to talk about, and depending upon your background and training, gravity or gravitation may invoke either Newton's apple or an Einstein's image, and the waves could again invoke image of a C wave or a sinusoid wave if you are you're undergrad, so you should be mostly thinking about these two than this, I think. So this is what I'll be talking about. These are waves produced by gravitation, and I'll be talking about what these are. So in what sense? Okay, let me just compare quickly. So we are really talking about gravitational waves compared to electromagnetic waves, which we have learned all in the school, and we know that spreads from the frequency, high frequency gamma ray, all the way up to the low frequency radio waves. And we do many things, starting from the optical thing where we see each other to communicating our phones and everything. So various bands of this have been used for various purposes that we know of, and we have a reasonable understanding from your school days itself about what electromagnetic waves are. And we know at the least that these waves are produced due to accelerated motion of charged particles. That is something that actually produces. And depending upon the method by which it's produced, the frequency could range anywhere from the gamma ray all the way up to radio. So now I'll be talking about very similar mechanism for gravitational waves, and I want to address the following very broad questions. So what are gravitational waves, and what are their properties, and in what sense do they resemble that of electromagnetic waves, and in what sense they do not resemble, and how do we detect them, which is actually a big challenge, which I'll come to. And finally, why should we be interested in gravitational waves? There are, in the case of electromagnetic waves, we use various bands for different purposes, including practical applications. So why should we be interested in gravitational waves? In the second part of my talk, I will also be talking about the historic detection of gravitational waves, which happened in 2016. And I'll be talking, giving you a flavor of that detection and why it is so so historical that made it grab the Nobel Prize. Okay, this is my broad goal. So let me go back to Newton. So we know that in the Newtonian gravity, which is what we all learn in the school, gravity is a force acting between two masses m1 and m2, and it's an inverse square law force to be more clear. It's always attractive. That means there is only one type of mass. There is no, unlike charge, which can be plus and minus, it could be repulsive, but it's always attractive. And the other important property is about the instantaneous action at a distance. That means that anything that you do now here, the gravitational effect of that is felt elsewhere, according to Newtonian theory, immediately, I mean instantaneously. So that means that the gravitational information, according to Newtonian theory, propagates with infinite velocity. That is almost instantaneous. Not almost, instantaneous in the theory. Of course. So this is something which actually was quite disturbing to Newton himself historically. No, that is what the Newtonian gravity is about. Then came Einstein, who made two jumps. Firstly, he introduced the special theory of relativity, introduced the special place for the speed of light being the kind of maximum speed you can attain, and the maximum speed with which you can communicate in the universe. That is the special theory of relativity, which also brought in the notion of space-time, which is, instead of thinking things as space and time as two separate entities, we can think about a common entity or a unified entity called space-time, where we have the three spatial coordinates, like we see, x, y, z, if you like, and the time coordinate, that's the clocks, where they are the clocks, and together they are embedded into the notion of one quantity called space-time. Right? And the important kind of departure from the gravity version of that theory, so Einstein, after dealing with the special theory of relativity, Einstein dealt with what is called general relativity, that is introducing gravity into the framework of the space-time, because in the original version there was no gravity, it was flat space-time as it's called, in the absence of any matter and so on. So the general theory of relativity is introduced incorporating special theory and gravity, and in that theory the kind of important distinction is indeed that there's a relativistic theory of gravity, in the sense that the signal speed in that theory of gravity can at max be speed of light. Again, that is something which actually I told you that there is no instantaneous action at a distance. Now everything should propagate at max with the speed of light. Now that is what is a big departure. So now we can think about waves, because waves is something which propagates from one part to another with a finite velocity. And the Newtonian theory couldn't admit waves, because anything that is happening here was felt instantaneously. There is no time delay, there is nothing. Whereas now we have a notion of a relativistic theory of gravity, where signals would be propagating with some finite speed, and that speed will allow the wave or any disturbance to be propagated at a finite thing. And that's why any relativistic theory of gravity would admit gravitational waves, not just GR. If you start with, if you want to account for a new theory of gravity, that will also be having the notion of gravitational waves, with signals propagating at some speed which may not be the speed of light in your theory, depending upon the details of the theory. So the important thing to keep in mind is that GR is a relativistic theory of gravitation, which admits gravitational disturbances to be transmitted at a finite speed, and these gravitational disturbances are what are called gravitational waves. So again, coming back to space-time, so this is a very famous thing you see about the, this is space-time in some sense, which is, in the absence of gravity, is flat. It's like a rubber sheet, if you want to think about. Depending upon the masses that you place on this, it will lead to curvature. And you can see that the amount of curvature will be proportional to the amount of mass that you accumulate. So this is the smallest one, this is the next one, and this is the largest one, and so on. So now, in this theory of gravity, Einstein visualized gravity to be equivalent to space-time curvature. And the curvature, the magnitude of the curvature would depend upon the amount of mass that you're talking about. So if you, again, think about it, this is like a sun, which is there, and this space-time around sun is curved. And according to GR, you would think the planetary motion, a different thing, will be in the curved space-time produced by sun. And any effect that we see in the planetary, everything should be explainable based on this picture of space-time. So if you if you model the planetary motions to be motions in the space-time curvature of curvature produced by sun, you should be able to explain almost all effects that we know in the Newtonian theory, and should be able to predict even more. That's what Einstein did, but I will not go to those kind of things. Instead, restrict to coming back to the picture of gravitational waves. So this is the important thing. So I got Einstein produced space-time plus gravity would introduce space-time curvature, and everything should be explainable based on how much is the curvature and the motion of smaller masses in the space-time of a large mass like that of sun here. And if there are questions in between, you can ask me, but we can also talk at the end. Okay, so in this new picture, we can have a simplified intuition or notion of gravitational waves. Now, there is something dynamical happening at the center of, there's some two objects doing something dynamically interacting, two masses. And this indeed, in the Einstein's picture, would be disturbing the space-time. So you can expect that there will be curvature of space-time will be changing. So that what that means is that depending upon how they interact, it is going to send out a wave or a ripple in the curvature of space-time. And this could be thought of as gravitational waves. This is one way of intuitively understanding what gravitational waves are. So something dynamical is happening at the center, dynamical in the sense of dynamical interaction of two masses, and that would indeed disturb the space-time around it. And this disturbance is what is traveling from the source all the way up to far away from the source. And these ripples are called as gravitational waves. So we now know that if you have two masses dynamically interacting, this is indeed going to disturb the space-time around it. And depending upon the nature of the interaction, it is going to send out ripples, which will carry the imprints of the nature of the interaction. And these ripples are what are called the gravitational waves in this picture. Right? So now you want to understand how would we think about gravitational waves. So if you have a passing gravitational waves kind of hitting us, so suppose we have a ring of masses, small masses, a ring of them to start with. Suppose gravitational waves are going orthogonal to the plane of the board, so that is going like this into the plane of the board. So it can be shown after a very detailed treatment within general theory of relativity that what gravitational waves would do to this is the following. As the wave this is a wave that I'm plotting as a function of time. As the wave goes on, it is going to deform a ring of particle which starts from circle to an ellipse along this direction, then back to a circle, then again an ellipse along the other direction, and then again a circle, and so on and so forth. So what it's going to do is to set a ring of particle into motion from a circle to an ellipse, back to a circle, back to an ellipse along the other direction, and so on. This is what the thing would do. It's like a tidal or differential motion. It is going to cause differential motion between the particles which constitute this ring. And so it's clear that, or based on the detailed calculation, we can show that a ring of particle is going to be deformed into an ellipse, and with a magnitude proportional to the strength of the wave. Depending upon how strong the wave is, the deformation or how large the ellipse is will of course be more. And this is what is going to be the observable effect of a gravitational wave that is passing to it. So of course, I have already assumed that the wave is passing orthogonal to the plane of the screen, which is important property in general theory of relativity. Gravitational waves are transverse. And that means it can cause disturbances only in a plane orthogonal to the propagation vector or orthogonal to the direction of propagation of the wave. So this is another thing. So just after the space-time ripple picture, if you happen to encounter a gravitational wave that is going by, it is likely to, not likely to, it should be deforming a circle, a kind of ring of particle into differential motion, and will be stretching and squeezing this particle as it goes by. Okay, so this is just to again play the thing. So this is a ripple of space-time that is going by. And what is shown here are, so we know that in the case of electromagnetic waves, there can be plus and X and Y polarization depending upon horizontal and the vertical thing, because you only plane left, and the two orthogonal polarizations are the X and Y. Very similar to that, you can show that the gravitational wave polarization, the state of the field, can be decomposed into two independent modes. One which will set the ring of particle into a shape of a plus, as you can see, this is like a plus. And another one at 45 degrees will be stretching it to a cross. So these are This again comes from detailed calculations in Einstein's theory of relativity, but the two states of polarization, very similar to the X and Y of electromagnetic waves, here is what is called the plus polarization and the cross polarization. Now, it is important to define the strength of a gravitational wave. So, how do we define the strength of a gravitational wave? Suppose you talk about you start with a circle, and suppose we talk about the one which lies along the x-axis. So, originally, before the wave was hit, it was at a separation of L. And after the wave, it is changing as a function of time. So, it is going to be delta L of t by L, which is the original separation. So, the ratio of the change in the separation to the original separation is called the strain. It's a dimensionless construction because some length by length, and h of t in some sense is equal to delta L of t by L. So this is the strength of a wave is captured in a dimensionless quantity called the strain, and the strain is defined by the change in the separation between two particles divided by the original separation. So this you can take into anything. In general, you could be getting a linear superposition of both of them. But in any case, what we are looking into is that if a wave is going by, it is going to displace two particles from the original position as a function of time, and that delta L by L is going to define how strong the passing gravitational wave is. Okay, so this is again how the wave would be propagating. So if a wave is propagating, it's going to distort the space-time along the thing, and it could, now we know that there's a differential motion, it could be doing various things depending upon how the thing will be. So you can see that the wave is going by, and it is distorting the space-time, and these are the different, this could be the initial, the grid points, if you want to say, is going to distort them, and this is the kind of effect we are going to see as the wave is going by. And we want to see, or we want to detect these waves which are going by. That is the challenge that I will get to soon. So far I have told you that in the Einstein's theory, gravitational waves are waves which propagate at the speed of light. They are produced due to dynamical interactions involving gravitating masses, and they are orthogonal in the sense that they can, any effect of them will be in a plane orthogonal to a direction of propagation, and the dimensionless strength, dimensionless strain h of t will capture how strong they are, and these kind of inductions are quite helpful to talk about what I'm going to talk about next. Okay, so this again to highlight this quantity which I have mentioned. I don't want to spend time here. So just again, it's good to compare because we know electromagnetic waves, at least we think we know, what are the differences between them. So important, gravitational waves are produced by accelerating masses in some sense, as opposed to accelerating charges that produce gravitational waves. And the interaction, so this is a big kind of big difference because gravity is the weakest of the fundamental forces. The wave produced by gravity interacts very weakly with intervening matter. So if you're looking into a source far away from us, it undergoes almost no interaction or no change as it propagates from the source to us. Whereas this is not the truth. We know that we know electromagnetic waves interact with various intervening things, can be lensed, dispersed, and whatnot, and so on. So I think this is quite a contrast with the thing that electromagnetic waves do interact with matter, whereas gravitational waves interact very weakly with matter. This is a very big challenge also because in order to detect gravitational waves, you also need them to interact with your instrument, and this interaction is very weak, and that is what makes the detection of gravitational waves a big challenge. So I did mention that both the gravitational waves and electromagnetic waves are transverse, so that is something which is common, whereas the other two are somewhat distinctions. Okay, I'll be talking about astrophysical gravitational waves for the most of the talk. I'll come why we need them. But I'll be talking about two types of sources. One is called a neutron star. So depending upon your background, neutron star is a star with a mass comparable to that of sun, like 1.4 times the mass of sun, composed mostly of neutrons, and is compressed to like 10 kilometers. So it's like a mass of sun you're compressing to 10 kilometers. That's what a neutron star is, and it's mostly neutrons. This is an end state of a star, so there are many stars we see around, And depending upon the mass of the star, one of the end state is called a neutron star. So the important thing to keep in mind that neutron star is a very dense star. So we can imagine one solar mass is compressed into the size of a city. That's as dense as it can get, and that's what a neutron star is. Another end state of a star, again depending upon the mass, is called a black hole. And black hole is something which we understand to some extent. We do not understand in some other words. Black hole is something whose gravity is so strong so black hole, simply put, is if the mass of a star is much massive, once the fuel that has been firing it, there are hydrogen burning and helium burning and so on, that is happening inside that. Once this fuel exhausts, there is an implosion of the star. And if the mass is high enough, it implodes into just one point. And that point is called a singularity, where physics sort of breaks down, at least the non-physics sort of breaks down. And that object is something, so from the gravitational field of that object, there is nothing which can escape. Even light cannot escape from a black hole. And of course, light can, we can see light from outside, but not from inside a black hole. And this is a black hole for the right reason, because since it cannot emit light like other stars, it is indeed black, and hence the name black hole. So black holes are extremely, it's as dense. It's like a density, if you think about conventionally, is going to be infinity, because only one point, a whole mass is at one point. And the inside region, no light can come out from this inside region, whereas if it can fall in, things can fall in, but things cannot escape. And this is what a black hole is. So you can see that the two types of objects I'll be talking about, both are very dense objects, and as we require them to have detectable gravitational waves, and this too is what I would be coming into soon. Yeah. No, differential motion, I said that with respect to center, if you go back to the thing. Yeah, it's nothing to do with differentiability, but this is to that. I simply meant to say that, yeah, simply along the one direction it gets squeezed, along other direction it gets stretched. That's what I meant by differential motion. It's like tides in some sense. Tides also does the same thing, and it's quite fundamental because the effect of gravity, in some sense, gravitational field is tidal in nature, and it leads to the differentiability. Simply means that along one direction it gets stretched, along other direction it gets squeezed. So that is a sense of differentiability. Okay, I guess there are no other things. Okay. So now let's talk about the challenges for direct detection. Sorry, I did not. Okay. So suppose we talk about, so we now know that we need accelerating masses to produce gravitational waves. Suppose we take a dumbbell, with both ends being 1 ton each, and with a separation 2 meters. That's something which we can hope to construct. Suppose we let this revolve around the center with 1 kilohertz frequency, that is 1,000 revolutions per second. So this is quite quite an extreme object that we can think of constructing on Earth. But if you calculate in Einstein's theory, what is going to be the h here? So the h, if you compute for this object, you can show it is of the order of 10 raised to minus 39. That means 1 by 10 raised to 10 and 1 and the 39 zeros. That's as small it is. Now, of course, there is one thing which is in our hand, that is original separation. So if you kept two objects, two test masses originally at 1 kilometer, that's something which we can think of. The delta L, that is the change in the displacement, change in the distance of these two objects, will be of the order of 10 raised to minus 36 meters. So it is, of course, extremely small, that we cannot hope to get there. To detect something 10 raised to minus 36 meter is not something which we can achieve at all with the technology we have. So what that means is that the kind of sources that we can, so though there are, any accelerated motion will be producing gravitational waves even on Earth, those will be producing extremely tiny, extremely weak gravitational waves which we cannot detect, so unlike electromagnetic waves. So I think that rules out the possibility of detecting anything that we can think of producing on Earth. and hence we turn to the sky. So astrophysically, like I said, if you two black holes which are orbiting around each other, so this is like a sun and sun-Earth system, but both of them being black holes, they are going around each other. That is indeed accelerated motion. So if that happens, of course, the space-time around that is going to be stretched and squeezed, and that is going to send out these ripples. And for example, if this kind of source at 100 megaparsec, so this is you can convert parsec to light. This is a reasonable astrophysical time scale, length scale where you do see things. At this astrophysical distances, the delta L by L is of the order of 10 raised to minus 21 if you calculate according to Einstein's theory. So again, going back to, if suppose you have two test masses separated by 1 kilometer, it is the typical displacement that this wave, due to this binary black hole, is going to produce is of the order of 10 raised to minus 18 meters. Of course, we have gained 18 orders of magnitude here, but still it is very small because it is 1 by 1,000 of a Fermi, that is size of a nucleus, and we are saying that if you separate two test masses at 1 kilometer, a passing wave, gravitational wave is going to change the distance by smaller than a Fermi, 1 by 1,000 of Fermi. So that is a challenge, but since we have improved by 18 orders of magnitude, people were bold enough to think how we can detect such very, very tiny displacement of the test masses due to passing gravitational waves, and that is really what started in the early 60s and 70s, who tried to think about how we can construct an apparatus or an instrument or an experiment which will be capable of detecting gravitational waves, which eventually led to the LIGO. Okay, so so we know that any chance of detection of gravitational waves have to be from astrophysical objects which are very dense, and that is why I went to the example of neutron stars and black holes, which are the most densest object we can think of, and they have to be doing something dynamically. Then our chances for detection are quite high, and it's 10 to minus 18 is as close to it as we can get. In the meanwhile, in 1974, so there was a lot of debate about whether how to detect these gravitational waves and so on. There was a strong indirect evidence for the existence of gravitational waves. And of course, the history of gravitational waves also had many complications about its existence itself and whether these waves are indeed physical, because Einstein's theory is a highly nonlinear theory of gravity, and the equations are too complicated. And Einstein himself at some point thought that these waves are some mathematical artifacts, not necessarily carrying energy, and it's not a wave of waves we think about in physics. But of course, things changed in the 60s with more rigorous work by Bondi and so on. But the kind of first indirect but strong evidence came from these two gentlemen who are observing two neutron stars. So neutron stars can emit light, mostly in the radio band. They observed two neutron stars. One of them is emitting light. They are going around each other, just like how I told the binary black hole. These are two neutron stars orbiting around each other. So what happens in this case is that because as they go around each other, there is a loss of gravitational waves. There's emission of gravitational waves. If they carry energy, you would be expecting the orbit to shrink. And if the orbit is shrinking, this would lead to the orbital period should be affected. So what these gentlemen did is that they observed the orbital period of this binary pulsar over years. And of course, this is they went till they got in 93 is when they got. So I think maybe 92 they had the data until here is what I think. They compared this solid curve is the general relativistic prediction for the decay of the orbit of the binary pulsar, and what is superimposed on them are the data points from the radio observations. So they found extremely good agreement with this decay of the orbital period of the binary pulsar being consistent with gravitational waves produced according to Einstein's theory of relativity. So they were confirming that indeed the gravitational waves are indeed being emitted, and whose existence can only account for this kind of a decay that they were seeing over the years in the orbital motion of the binary pulsar. So, not surprisingly, they were awarded Nobel Prize in 1993. And of course, it is to be kept in mind that we are really talking about two pulsars very, very far away. That's what we are talking about. But now it's important to think about what will happen afterwards. So after, if you think about the mechanism, it is going to lose energy. As it is losing energy, it is going to come closer. As it comes closer, it is in a stronger gravity because they have been now gravitational field is stronger. Then they emit even stronger, and then they even come closer. So the process of emitting stronger and being closer is like a runaway process until these two objects eventually merge to form a single object. So what they were seeing is like a very early phase of it, two neutron stars sufficiently far away, going around each other, and orbital decay of them. But if this process continues for millions of years, actually, we would be seeing them, at some point, we will be seeing them to be merging and forming a new object, maybe a black hole. These are two neutron stars, and the mass would add up to what is called a black hole. Of course, this will take millions of years, so we cannot see them merging. We won't be alive till then. But if this object exists, there may be many other objects in our universe which will be like this, but maybe in the very late stages. So the process of inspiral, that is the process of them coming closer to each other, should be existing in nature, and we should be able to, if you are able to devise an experiment, the merger, that is the process of them coming to form a single object, should be detectable on Earth by some experiment. If we can construct the experiment along the lines of that can detect 1 by 1,000 of a Fermi displacement. So this was a very strong boost to the efforts to directly detect gravitational waves, in the sense we set up an instrument and we look into the displacement produced by gravitational waves and give a very strong boost to them, and that is what really carried out since late 1970s. So this is something which I want to come closer to. So what I'm talking about is that you got two black holes in this case, or neutron stars. Both will be good enough for us. So these two objects go around each other. So initially they are almost like sinusoid wave, but if you observe them closely, what will happen is that both the frequency of them will increase because they are going now faster around each other, and the amplitude will increase because as they come closer, they are emitting stronger, and the strength of the signal will also increase. So the waveform expected according to Einstein's theory is something that is called a chirp signal, where as it evolves with time, both the amplitude and the frequency increases as a function of time. And this will go on, so this is the early phase, and this will go on till they merge. That is where the maximum strength is. Now, once they are merging, they may still be settling down, so there can be still some accelerated motion of this new object, which can give you a very quick signal which damps very quickly. It's like a damped sinusoid, and this, the accelerated motion of this newly formed object giving gravitational waves is called the ring down. So there are three phases. One is inspiral. This is this almost monochromatic kind of a wave, and merger, which is the late stage when they are very close to each other, almost in physical contact. They emit the strongest. That's called the merger. And ring down is this new object that is formed. It's undergoing some kind of complicated rotation and acceleration, and can give you gravitational waves, and that is what would give you the ring down. So these are the three phases of binary evolution: inspiral, merger, and ring down. And the strongest emission, as you can see, is from this late stages of the inspiral and the ring down. And what binary pulsar observed is like much, much earlier in the past, in the millions of years ago. It was completely monochromatic almost, and that is the phase that was seen indirectly in the case of binary neutron stars by Hulse and Taylor. Okay, this is simulation. Simulation meaning you try to solve the Einstein's equation numerically on a computer, not on a computer, on a computer cluster, and you try to see how the gravitational waveforms evolve as a function of time. And this is by a group called Simulating Extreme Spacetime, who did the simulation. So what I'm going to show you is the cartoon of two black holes going around each other, and as it will progress, you will see that the gravitational waves would be, this is the strength of the gravitational wave that I will be showing. So these are the two black holes, and the strength of the gravitational field on the space-time is what is shown below. You can ignore them, don't worry too much. You can see that as they come closer, this is the red one going, they come closer and closer. You can see that they go faster, and this process will continue. Yeah, now you can see that they're in the very late stages almost. You can see a sweep, increase thing. So this is going very fast. and they come so close to each other that almost they are in physical contact. Yeah, so this is a new object that is formed, and that now, so we are just stopping there, this gives you a ring down. So that is the late part of it. Now there is nothing that after that. So this is really the situation. You've got two objects which are going around each other and producing gravitational waves, and what I showed you on the waveform that I showed you was actually really solving Einstein's equation, though the black holes I was showing was like just to show where the black holes are. So these are, before I go to some more details and so on, so why are we interested in gravitational waves, right? We can see clearly that gravitational waves are unique ways to measure the mass of neutron stars and black holes. Black holes, we have very, very indirect way of measuring the mass of black holes. But here we are going to see gravitational wave signal whose strength is going to be proportional to the M1 and M2 of the two black holes that it composes of. And it will give you a direct measure of the black holes. Of course, it can also be used to understand how the binary was formed astrophysically, because there are many problems in astrophysics which will need to be invoked to explain the formation of a binary system, which eventually become a black hole. Of course, if you observe them out to large distance, you can understand the universe. And of course, if you can, with very specific dedicated detectors, you can go very close to the Big Bang, where the gravity decoupled from the other fundamental forces. It would have given you a background very similar to the cosmic microwave background and so on. You will be able to detect them. That's again much into future. And finally, a very interesting question is that we can ask, because now we know very accurately how the gravitational waveforms are in Einstein's theory of relativity. By observing them, we can ask the question that, was Einstein's theory correct? Did it have all the ingredients correct, or is there any deviation from Einstein's general theory of relativity? So these are a few avenues that are of interest to us in terms of why we want to, or what we want to use gravitational waves for. So now just coming back to the problem, I told you that it's about test particle of 1 kilometer. You have to have a very tiny displacement, and this quite a challenge. So you can see, imagine that you're talking about 1 by 1,000 of a Fermi, and many other things, the ground vibrations and a car going by, many of these things could be producing larger displacement. So you have to have a mechanism to isolate other disturbances from the system, and we measure the system and call whether this coming from a binary black hole or not. So I think the challenge is how to detect such a tiny displacement in a sea of various types of noises that would contribute or mimic the signals you are expecting. So that is what is achieved in these detectors. These are 3 operational detectors, 2 in the US, it's called LIGO, Laser Interferometric Gravitational Wave Observatory in Louisiana, in Livingston, and Hanford in Washington State. And the one below is a 3 kilometer arm length. The arm lengths are 4 kilometer each for this. This is in the Europe, in Italy. It's a European, many European countries contribute to it. So this is like 3 kilometer long arms, comparable to that of the 4. For geographical thing, they chose for 3. So these are the large scale laser interferometric gravitational wave detectors. And the question that I asked in the last time, how do we detect such tiny displacements, is really answered by what is called the interferometers. And maybe you've done a laser interferometer experiment or Michelson interferometer experiment in the laboratory, but I'm just going to show you how the LIGO works. So the interferometer, as the name indicates, is going to measure interference pattern, and we know there is destructive and the constructive interference. And you can always adjust the path length between the arms of this interferometer. So this is the L-shaped one, and this is a beam splitter. Light is going to come from here, is going to split here, come back here, go back and come back. And the light reflected back from here is going to undergo interference here, which will be monitored in this screen. And originally, you can adjust the length light travels to both sides, and just make sure that there's dark fringe or destructive interference. But eventually, as the gravitational wave is going by, you would expect the arms to be stretched and squeezed. Hence, as the arm length changes, you expect your fringe is no longer dark, and you would expect some light to be detected because it's not no longer completely dark. So this is the light coming in, gets split, comes back, interferes, and hits the kind of beam, the kind of photodiode. as it gravitational wave hits, it shakes not so vigorously, but it gets there. So from the light wave perspective, you have a wave that gets split into two. They go to N mirrors, get reflected, comes back, again interferes here. Originally, they cancel, so there is a dark fringe. But as the N mirrors shake due to gravitational waves, you can see that they can lead to interference which are not completely destructive, and that will give you a light at the photodiode. So the light, you can see that as it goes, there is some light at the photodiode. Initially, you were tuned it to be dark, but there is some light. Of course, this is all good in terms of theory, but the question is that how do you know that this light that you're seeing is due to gravitational waves? Because we know that many ground motions and many other things, circuit complications and so on, can also produce or displace the N mirrors, and that can also contribute to this light at the photodetector. And the real challenge for a data analysis of gravitational waves is to claim confidently that this light that we are seeing, or the signal we have seen, is strong enough, and argue that this has indeed come from astrophysical origin or astrophysical objects such as black holes or neutron stars. I will not go to that part until there are questions from you, but I just want to explain that the way, the clever, of course, this is only basic design. There are many techniques they use to achieve this 10 raised to minus 18 meter sensitivity that we talked about. But basically the LIGO, how LIGO functions is like this at the very crude level. So one interesting thing to think about is, if you think about the frequency of the LIGO black holes, this kind of thing that we see, it ranges from 10 hertz to a few kilohertz. You can see that this is in the audio range. This is again the frequency that we hear, that we listen to, right? So one interesting thing that is often used to express or to show what gravitational waves are, to actually plug in the gravitational wave signal, like the one I showed you, to a converter, and you just listen to it. The question will be that in the noise background, how well can you detect a gravitational wave signal by just listening? So I'm going to play some audio for you, but I want to warn you that this is not how we do the data analysis. This is only a way of kind of conveying the audio perspective that of gravitational waves compared to light. So light, in some sense, helps you see things, whereas gravitational waves is very complementary, and it is like listening to a signal. But data analysis done much more, using much more complicated techniques and so on. So what is shown here is the sensitivity, or this a noise background. That is, only if the signals are above this noise, you can see them, or you can detect them using an interferometer. That is something the data analysis guys would be hoping to do. So just based on this, let me go to the thing and just play the. So of course, I'm going to play 3 different types of audios, and so they will be characterizing different types of signals with different masses and doing different things. So just to understand the diversity, so this is one signal. So you've seen a beeping up sound. So I told you that the frequency of the gravitational waves increases as a function of time, and that is what causes this increasing thing. Just to listen to it again. So it's a very short chirp, like what LIGO would see in the typical LIGO thing, may be lasting for a few seconds, and that is what you have heard. So again, depending upon the masses and so on, it could be. So the last thing is, of course, very loud part of it. The last is, as we saw, the strongest part is indeed loud. But what I want to notice here is that there are some modulations to it. So if you just listen to it, there's ups and downs even within the signal. It's not so straight like in the previous one. So though the N part is really loud, but there are, the sign is not, though it's like a wave, there are ups and downs or the modulations of the wave, which can be produced due to the various things that the system does, which I will not go to. But what I want to argue here is that by detecting these waves with different spectral properties, is a way of probing various mechanisms or various physical effects that these objects will be exhibiting. So let me play one more before I go to the... So in this thing, it's even more important. You can see that there are even stopping, for some time it even stops and so on. So the modulations or the details of the gravitational waveforms is a direct signature of the signal or the physical effects that the system shows. And hence, this kind of waves, if you do inverse mapping, we should be able to understand the dynamics of the system much better. And that's what that's what we hope to do by detecting gravitational waves. Okay, and if you are interested, you can go to this website called Sounds of Spacetime, which has got many sounds for different systems. They also explain what kind of sounds, what are the systems, and so on. So if you are interested, I would strongly recommend you to Google for Sounds of Spacetime and play some sounds there to get a feel for what gravitational wave signals, what kind of sources will produce what kind of gravitational waves. Okay, so in the last, I don't know, 5-10 minutes or so, I will be talking about the discovery of gravitational waves. So I told you that since 70s, there was a lot of ongoing effort, started the efforts to build a LIGO detector. And it is very complex. They had to first design an instrument, and by 80s, their first design was complete. They did a small prototype. In Caltech, they had a 30-meter prototype of LIGO. They sort of showed to the funding agencies that this will work with that sensitivity. Of course, they didn't detect anything, but they showed it can function. Then it was the full LIGO was funded, which the 4-kilometer thing that I showed you, which had one science run with the so-called initial LIGO configuration, which was not good enough to detect any gravitational waves, ran for about 8-10 years. But then it was shut down. Then LIGO was upgraded to what is called advanced LIGO, which is even more sensitive, and it was clear that this advanced LIGO sensitivity should be good enough to detect the gravitational waves according to the astrophysics that we know, and hence was extremely exciting. Of course, this is something which we are searching for the first time. We do not know the rate of these events and so on. So there was a lot of bets happening about when advanced LIGO will detect the first gravitational waves and so on. Some people said that LIGO will never detect it. Okay, and then the question was that if you did not ever detect, what does it mean? And so on. There are all pessimists all around, as you know. But I think some people did expect to see it in a year's time or 2 years' time, because they knew that it will take some time for the instrument to stabilize and so on. So they were the most optimistic people expected a detection of gravitational waves to happen in a year's time or something from the operation of LIGO at the advanced sensitivity. But what happened was quite interesting. So LIGO, advanced LIGO, the official science mode run, data taking was supposed to start on 15th or 14th, on September 2015, and the previous day, as they were about to finalize the configuration of the detector and interferometer mirrors and so on, they detected actually a very strong gravitational wave signal. So that is called I'll go back to the thing. So 150914 would mean 2015 September 14 is what that means. So okay, so 14th is when it was detected. So 15th was when it was officially supposed to start. So even before LIGO started taking data in the officially as advanced LIGO, we were fortunate to get this signal, which I will come back to. So this signal apparently, after studying it for about 8 months, it was inferred that this was emitted 1.3 billion years ago. So that is 10⁻⁹ years. Of course, if you think about the situation on Earth, life was just getting formed on Earth at that point, and we were in all the form of bacteria or some kind of stuff. And this was produced by the collision of two black holes, which I showed you, the binary black hole merger. And it traveled all the way during this time and hit the LIGO detectors on 3:20 p.m. Indian Standard Time on September 14th, 2015. And that is the time it took to travel. By then, we had evolved from very primitive objects to human beings and capable of setting up an instrument to actually detect them straight away. So there are 2 LIGO detectors, which actually is used to, you should have a signal in both of them, if it's true, because the noise features are so strange that we want to be sure. So the 2 LIGO detectors operational at that point of time detected them with a good strength. And this event, so this is, and of course, as you can see that after it was detected, it took around September is when it was detected. Officially, the detection was announced in February. So until then, around 5 to 6 months, and the LIGO scientific collaboration was investigating this more and more to make sure that they are indeed astrophysical in origin, what are the masses, what could have formed it, and so on. So very detailed study of the signal happened before this was kind of announced 6 months after, roughly 6 months after this was done. So what this event is, so this 150914 is what so GW stands for gravitational waves, and September 2015, sorry, 14 September 2015. And what we were seeing is actually 2 black holes with 30 solar mass and 35 solar mass, that is the 2 black holes. They merged to form a 62 solar mass black hole, and around 3 times the mass of sun was emitted in gravitational waves. So that is as huge an energy. So the most of this energy of 3 solar mass would have happened in the last fraction of a second, and that much of energy is emitted in this merger. It's very violent relativistic merger, and when they're merging, the speed of them are roughly the speed of light, or half the speed of light. That's 2 black holes sort of hitting each other at relativistic speed is what was being seen. And what I'm going to play next is actually the sound that produced, is again to compare. This actually, the actual data with some very minor filtering is being fed into an audio system, and this is how the audio would play. Yeah, so the last beep or the bum, the kind of the thunder-like sound is what we could hear, because very high mass, and this merges very early, and this very loud signal gave you that loud beep or loud sound, and that's what that's what we saw. So what is shown here is actually the plain data without any analysis. So it just stands out like it is. There is nothing to be used, and this is almost like a signal that you would expect from GR, except for some noise-induced distortions, and that is what was really kind of detected. And this is very good because it's a very strong signal, which is good to, when you have a weak signal as your first detection, you have to really fight to establish that it's indeed astrophysical in origin, whereas this is a very loud signal, and which is fortunate. And this is what was detected. And we estimated the masses and so on, depending upon the signal characteristics. Masses, spin of the black hole, etc. were estimated, which is... So this was, of course, a significant milestone in astronomy. This was like a first direct detection of gravitational waves. Again, inaugurated a new branch of astrophysics, because now we can use the black holes and neutron stars using gravitational waves to probe details of their masses and how they were formed, etc. So this branch of astrophysics is called gravitational wave astronomy. Of course, this is the first direct detection of black holes in some sense, because we have seen them indirectly through accretion and other phenomenon. This is the first observation of a binary black hole merger, and again, this is like a first, we could do extensive series of tests of GR. So we could ask the question that how well did the detected signal agree with the predictions of Einstein's GR, and indeed, in a very highly relativistic and radiative regime, and we found excellent agreement with the predictions of GR. So it's one more big thing to GR, that it was shown to be valid in a regime where it has not been previously found to agree. So it's a very unique way of probing the highly relativistic regime of the merger of 2 neutron stars. So again, given the kind of groundbreaking nature of this thing, it got several awards, starting with the 3 people who worked. Ray Weiss, who is really the one who devised or made the map for LIGO, and Kip Thorne, who did several theoretical development, won the Nobel Prize in 2017. for this historical discovery. And again, many awards followed, which includes some of them which you may not even know, but I think they're quite very highly regarded awards in the field of astrology, cosmology, and astrophysics, and so on, in the year 2016 and 17. So this is quite an achievement. And what followed later on was even more interesting. As the data taking sort of continued, what happened is the following. So we knew that we had detected a binary black hole, but we also know that we should be able to detect the binary neutron star, the last stages of the Hulse-Taylor binary pulsar type systems. And that is what happened on, now you know, this is on 2017, August 17 is when this event happened. And what is shown here is the time frequency map of the signal. We expect the frequency to increase as a function of time. You can see that in the two LIGO detectors, there is a long in spiral. This is very clear. This is not so clear. And this is the two LIGO signals. Virgo did not have much of a signal, but it played a role in a different way, which I will come to if there are questions. And what happened is not just this. This is the first detection of binary neutron star merger. But unlike black holes, which cannot emit light, the neutron stars are known to, the merger of neutron stars have got a lot of neutrons and other matter around it. It is expected to emit light also. So it is known that this, the source of the gamma ray burst is a burst of gamma rays which was seen in 60s. And one class of them is called a short gamma ray burst. They were hypothesized to be due to the mergers of neutron stars, but that could not be checked. What happened after this is that soon after this sort of ends, so this is the plot of, this is a Fermi satellite, it's a gamma ray satellite which is capable of detecting gamma ray burst. The moment it so the LIGO thing would have ended at 0 here, like less than 2 seconds after the barium neutron star merger happened, the Fermi detected a spike in its spectrum, so that actually is a gamma ray burst, as it is called. And lasted for less than 2 seconds. And this, of course, meant that, so what is happening is that two neutron stars were merging to form a black hole. That black hole was sucking up matter from around. It was giving you a jet-like thing along, along the line of sight, if you wish. And this jet is what is causing the gamma ray flash that we are seeing. So this jet is only the gamma ray, but what will happen actually is that as the jet is going through the interstellar medium, this jet will be slowed down. As it slows down, it imparts acceleration into the interstellar medium or the charged particle or the plasma in the interstellar medium and will emit in every band from X-ray all the way up to radio. This has been seen in short gamma ray bursts, but never seen in coincidence with the gravitational waves. So for the first time, this was the detection of gravitational waves and the electromagnetic waves here. And after this, we observed the system in all the bands, starting from gamma ray all the way up to radio, by extensive observations by astronomers, which lasted for 3-4 months, and even some of them are still continuing in that patch of sky. So this is probably the most extensive astrophysical, astronomical search for any object, which was followed up by these electromagnetic waves. And we, as a result, we detected emission from the system at almost every band of the electromagnetic spectrum. So for the first time, we were sort of combining electromagnetic waves and gravitational waves from the same system, and it did give immense amount of information about this phenomenon, which again is too technical for this talk. But it is important to keep in mind that while the previous one was a binary black hole merger, this one is a binary neutron star merger, and we also found a light associated with that in various bands. And since then, I'm showing you, in the until this April, last April is when the third observing run started. So first one is in the first observing run, and during the first and second observing run, which lasted for around 6 months, we detected several binary black holes. You can see of various time frequency maps. So the frequency evolution is shown here, and the waveforms are shown here, and a binary neutron star merger. So we had detected 10 binary black holes and a binary neutron star merger, and that is what we have seen until the end of second observing run. And the third observing run, with more improved sensitivity, started in April and continued till September. And now it was undergoing a one break in October. It's again starting. So the O3, as it's called, observing run, this is still continuing, and we have got several interesting candidates for binary black holes and binary neutron stars, which are being studied, and more detailed things should come in the next few months or so. So now it really means that LIGO and Virgo detectors are in good shape to really detect many of the systems and start doing very interesting astrophysics, which was not possible otherwise using electromagnetic wave observations. So in future, we are going to have a very interesting set of things. So this is the two LIGO detectors I mentioned about, Livingston and Hanford, and Virgo is the European one, and Kagra is actually in Japan, and that is being now commissioned. They are actually trying to come up. They are doing some first kind of runs, and this should be joining. So these 4 detectors will be joining in the next 1 year or so. All of them will be functioning together. And LIGO India is an approved project. That is to have a LIGO-like detector in India. It will be in the Maharashtra. The site is now site is taken over, and we'll be constructing a LIGO-like detector called LIGO India, which will be operational maybe in another 6 years or 8 years, depending upon how optimistic you are. Right? So this is going to be really the future, that many detectors are going to come up. They're going to look into the sky together and observe them and understand various interesting things which were not known earlier. And already the third observing runs could be giving a lot of surprises with respect to standard astrophysics that we knew. So it's going to be a very interesting future for the gravitational wave astronomy with all these detectors joining and so on. Okay, I think I have short my time, so I'll just conclude here that so the gravitational waves are like unique messengers of the cosmos, which really complements light, as we have seen in the binary neutron star merger, in a big way, and together they can give very complete information. And first detection of gravitational waves had a significant impact on our understanding of the nature, and so was the binary neutron star merger. And LIGO India, Indian detector, LIGO detector in India is going to play a big role along with other detectors in the years to come, and the future looks very bright to look forward to. With that, I think I'll stop and I'll take any questions you have. Thank you so much. Yeah. Yeah. No, so cosmic microwave background is when the electromagnetic radiation decoupled from the other fundamental forces, we get a relic around that, right? And the gravity would have decoupled much, much earlier, like a fraction of a second after the Big Bang. Electromagnetic waves happen much later, and if you can detect the CMB-like background of gravitational waves, that is called the primordial gravitational wave background, that is going to tell us a lot about Big Bang, inflation, and so on. So that is what I meant. The very early stages of after Big Bang, what happened, will be imprinted on the CMB-like background that the gravitational waves would have left, which we have to see, of course, to detect them. But unfortunately, that typical frequency, because they would have been redshifted so much from the past, they will be happening in a frequency between 0.1 hertz and 20 hertz. That's a rough estimate. And you may need a dedicated detector which will operate in that regime, which will be for future. But once these established technologies are known, one should be able to do that, maybe in the next 20 years time scale. But even then it's worth it, because we are going to get a very close look into all these things in the future. Okay, cool. So that is the clearest talk I have ever given. So only one question. Yeah. Yeah. Yes. So it's not about unification. Is not about. So see, as the Big Bang happened, after the Big Bang, things were decoupled. So different fundamental forces were decoupling, right? And the unification is an attempt to go into the past of the universe where they coexisted. So to understand the universe in the very early stages, you need to have a very unified picture about all these fundamental forces after the Big Bang, they were all together. And to understand that phase, you need to have a complete, you need to have a theory like that. It's not about studying them now. Now they are all, we can study them separately. It's about early universe and how we understand early universe. You need to unify them, go back into the past, and understand what would happen. What is Big Bang? We still don't know. How it happened, what was the properties, and so on. So to answer some of these questions, we have to go back into the past where things were all together. And you have to go back with the theory and think about what the properties of the unified theory is to understand that. That's all. Yeah. Yes, grand unified theory is a hypothetical theory which will supposedly unify all these fundamental forces. That should help us in everything once we have it. That's like but I don't know when that will come up. Yeah. That I'm not sure, because the gravitational waves are going to give us only insight about the gravitational force. And even so, the gravitational waves I'm talking about are purely classical gravitational waves. In the sense, we know that we don't need to think about electromagnetic waves as photons to explain gravitational waves. Maxwell didn't know about photons. So we are still in the classical, that regime where the gravitational waves are classical. And even, only if you come up with a very specific quantum gravity models, will you be able to use gravitational waves to even probe quantum gravity. So leave alone the other fundamental forces. So it's it's not going to, the direction of primordial background or inflationary background is not going to give us any insights into the grand unification part of it. That has to be separate, because we are not sensitive to the other fundamental forces a priori. Yeah. 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 Yeah, so I think, there are two reasons for it. First of all, the advanced LIGO, LIGO as an experiment, as a project advanced faster, and the sensitivity that is up to what distance LIGO can see is more than that of Virgo at that point. Okay, that is the first thing. But secondly, it can also happen that if because we have Earth and the source is on the sky. Depending upon the where the source is in the sky, different detectors may have different responses to that part of the sky. That's antenna pattern kind of response. But that is what is important here. Even if the sensitivity was low, even with that sensitivity, the fact that Virgo did not see anything had to do with which part of the sky it would have come from. And that was quite important, because when we use Fermi has to, Fermi or doing electromagnetic follow-ups, they can look into very narrow patches of the sky. So because the two LIGO saw this and Virgo did not see it, gave you very accurate location on the sky where the source would have come from, which helped actually the electromagnetic follow-ups, various detectors, X-ray, optical, and so especially optical, because using optical one could pinpoint the galaxy from which it came from, only because this together it told which part of the sky it would have come from. That is quite useful. So it is about the smaller sensitivity, and even with the sensitivity, only the source would have come from some patch of the sky would have this situation arise, which helped us understand what the thing is. Yeah. Yeah, so I think this is a thing which I skipped, but I'll show you. So this is a technique called mass filtering, which is this. So see, what we're actually looking for is, because of, since we know the gravitational waveform in GR very accurately, I told you either theoretically by numerical simulation, what you're looking into is that there is a signal like this, which is actually buried in a noise like this. So this is a very small thing somewhere here, right? This is what we are looking for. Now what you do is the following. Because we can construct gravitational waveforms, as among M1 and M2, let's say, the binary. Let's take non-spinning systems. So for every M1 and M2, there is a waveform that you expect. In a search, let's search from 1 solar mass to 100 solar mass. And now, suppose you construct a grid of 1 solar mass to 100 solar mass, every point is like a waveform. You can compute a waveform on every point. Suppose it's analytical, then you can almost analytically compute every point. Now what you do is the following. So you take this data, which you don't have a signal at all or not. You cross-correlate this data with a bank of templates corresponding to these points. So each point you do. And at a point where the signal is actually buried, your correlation function will be peaking, because that actually matches with the signal there. You get a peak in the correlation function, and that correlation function has to be, so suppose this correlation function is peaking here. This is above, the background is like 2, and this is peaking at 10, right? It's a factor of 5 times more. It's very strong peak. Suppose this peak was here. Then, of course, it's a weak detection. You don't know whether that is from the noise or not. So the signal-to-noise ratio is dominated by this, in some sense, how large is this peak in the correlation. And depending upon, so this is a very strong signal. It's very unlikely. So for example, the first LIGO detection, you can say that the probability of that signal being from the instrument is less than 10 raised to minus 9. So that is that small. They can do this characterization only because we know the signal very well, and also noise to some extent. So given the property of the instrument and the signal we are expecting, we can quantify this. It's actually a very detailed thing about how we exactly quantify, but intuitively we use the best knowledge of our waveform. And actually quite a challenge, because that means we need to have a very accurate waveform model to do this thing very accurately. So this technique is called match filtering, which is what we use to do the analysis. Is this clear? Yeah. Yeah, so I think basically they are classified into 3. So there are, at the low frequencies, you got seismic noise. For example, the ground, if you don't look into anything, ground itself is vibrating with some frequency. There may be cars going by, gravity gradients, maybe helicopter, aeroplane going about LIGO sites and so on. So there should be some way of screening all these things. So at the low frequency, you are, this one, right? Yeah. So at the low frequency, if you draw a line like this, this is going to be due to the seismic thing, up to some 60 hertz or something. Now at the mid frequencies, I told you about the LIGO mirrors are what is reflecting. You're suspending this, suspending the LIGO mirrors, and suspension is with some wire, right? Some wire, and the wire will have KT noise. It'll be there'll be a random vibration of the electrons in the thing, right? Very small, agreed, but we are looking for something which is 1 by 1000 of Fermi, and this random motion in the electrons of the suspended wire will be giving you some noise. At that frequency of the noise will be here. Of course, you can suppress them by using cryogenic technology. That's what Japanese people are planning to do. Cryogenic technology, go to very low temperature, where this is almost frozen. Of course, it's too expensive, but if you don't do it, you're going to get some noise here, there. And the high frequency, you're going to use lasers, and photons are being hit and so on. So at very high frequency, there is an uncertainty in the counting. So how many photons are hitting the thing? There's an uncertainty called photon short noise, and that that can be suppressed with using high power lasers. If you use very high power lasers, the mirrors might get damaged. So it's about the uncertainty in the counting the number of photons at a high frequency. So basically, low frequency is seismic noise, mid frequency thermal noise, and high frequency is laser photon short noise. Of course, this on top of all the other circuitry will give its own thing about the thing and so on. This is broadly the classification of the thing which would come down. And so right now it is only here. So the hope is that with the kind of future detectors, maybe third generation detectors beyond advanced LIGO, they want to go till 1 hertz. But beyond 1 hertz, you cannot go on Earth at all, theoretically, because the ground will be very strong wall beyond less than 1 hertz. If you want to observe anything less than 1 hertz, you have to go to space. And that is also planned. There's a planned laser interferometry space mission going to be operational in 2032, which will be actually a space-based mission in the 10 raised to minus 4 to 0.1 hertz, millihertz regime, which will be observing supermassive black holes, because the mass scale is now different, not the stellar mass one, not this 30 solar mass and so on. You'll be seeing galactic mergers. Galaxies have got supermassive black holes at the center. They will be going around each other and merging, and those mergers will be seen by those detectors. But that you have to wait till 2032. Now it's a funded project. After LIGO did not detect, they were not very positive, because both the European Space Agency and NASA were together initially. But NASA at some point unplugged their support. But after the LIGO, now it's likely that it's going to be a joint project again. So it's an approved project, definitely will fly off in 2032, and we'll see what happens. But that is probably the closest it can come to detecting any hints of the primordial thing also, because it can go to the 0.1 Hertz regime. And if our theoretical models are not so correct, we may be seeing actually background in the high frequency end of CLISA. But again, if you want to go for the detector I told you about, the 0.1 to 1 Hertz, you would again, it's like a 3 LISA detectors and so on, which is extremely complicated, but that may be again 20 years after that. So maybe 2050 is when you can hope to that. But at least the science cases for them are clear. It's about the instrumentation and funding that has to be done. Yeah. Not geography. The only this is LIGO. The only geographical factor which has gone in is that you want a large baseline. Yeah, you can see that this is the longest straight line you can draw in the US. They want it to be as far apart as possible because that will give you a large baseline. And that is what they chose it, but all other things are, for example, India, we have to, and what they optimize is you need to have a low seismic noise zone. So for example, LIGO, the LIGO India did a site survey across all states, including Tamil Nadu. They wanted to try to see if something can be done together with the Neutron Observatory and so on. Of course, the hilly area, they had their own complication. Finally, what they prefer is a flat land with no seismic, background to be the least. And also, finally you're going to set up an experiment. You need some cities close by, but not so close by. So it's a very practical versus scientific trade-off. And finally, they ended up with the town called Nanded in Maharashtra. It's at the right Hyderabad, Maharashtra, Pune, Hyderabad highway, and some deviation from that. That's a complicated trade-off between practicalities. Should be that all the seismic noise should be the least, and other things also. In terms of, it should be, scientists are going to stay there to set it up and so on, should be accessible. And also, you shouldn't have I think even LIGO, or there's one of the Hanford one is in the forest. And there's a background of the tree cutting in the thing is actually a background which they cannot get rid of. So I think at least some isolation is good, but not so much that people cannot even live there. Okay. No, we would love to have something in the southern hemisphere. When we want something in Africa, I mean, there is. I mean, we should get funding. It's thing by funding. Actually, the LIGO which is coming to India, they wanted in Australia actually, and actually, because so historically there were 3 LIGO detectors in the during the first phase, of which they shut down 1, and that's what they wanted to move to somewhere where they will maximize the science impact. But Australia did not give the support. Then they contacted India, and India could, Indian government could support. That's mostly driven by, political and nothing to do with the. I mean, it'd be as spread out, like I said, something in, somewhere here or here, in the somewhere in Brazil, for example, would be good, or somewhere in Africa. But there is, somebody should. The funding is a issue. Nothing. Yeah. Okay, good. So it is a good thing, and you can talk to me, of course, later on if you have questions. And do go to his site. Sounds of Spacetime is a fun site. You can go and play the sounds there. Okay, thank you so much.
Thank you, Professor K.G. Arun. It was such an interesting talk, and you gave a lot of information on gravitational waves to ponder upon. And thank you again. And our next talk will be Professor Sharat Sane on the topic mathematical games at 2 o'clock. Thank you.